Hello. Now let's look at the third and last part of the electric motor secret, the film by Peter Lindemann. It is about the circuit details, patent from Roger Anderson and John Bedini and some other implementations. And also he is talking about the magnetic circuit and his own ideas how to implement and how to improve the performance of the electric motors.
Now here is a patent from 1974, and it was issued to Roger Andrews, and it's called Novelty Electric Motor. And this is the basis of many of the very successfully marketed executive desktop novelties from the 1970s and 1980s. So what I'd like to do is give you a close-up of this very interesting circuit. So here is the cute little masterpiece of Roger Andrews. And this shows in the drawings, figure 1 and figure 6, two of the most successfully marketed versions of this toy. And we can look at this one in particular. This consists of a plexiglass kind of rail like this, and this wheel has a number of magnets on it and a very small shaft, and it will roll back and forth and back and forth. And this was very successfully marketed as an executive desktop novelty called the Space Wheel. And what I'd like to show you is this little circuit. The one above was presented as a little table that had a top that would spin on it. And what was novel about this is that you'd start spinning this. You could start to spin this top, and it would spin for 8 months on this little thing. And it looked like a perpetual motion machine almost. It would just spin and spin and spin and spin and spin. And the circuit, and of course this would rock back and forth for literally 7 or 8 months on a battery. And he was just using a 9-volt little radio battery to run these things. And essentially, if we look in figure 1, we can see that the circuit consists of a battery, and a single transistor, and an inductor with a split winding. And that's the whole circuit. And how this operates is that there are magnets in the wheel, or in the top. This is the version that has the top. And the table was sloped down and had a low point here, which was in a ring, and then a slight rise in the center, and then rise out to the center, to the other edge. And this was a circular table. And so the top was free to kind of move around anywhere, but its preferred location would be right here in this low dip. And what that would do is it would put one of the magnets periodically right over the central inductor. And what would happen is that when the magnet would go by, it would induce a small current in this coil, and that would place the proper inductive polarity on this transistor and turn it on for a brief moment. At which point, current would be conducted from the battery through the coil. It would reverse the polarity of the magnetic field in the inductor, give a little bit of a kick to the top to keep it spinning, and then that reversal would also reverse the conditions on the base of the transistor, so that would turn the transistor off, so then the current would stop flowing and the magnetic field would collapse and generate a little bit of a back pulse. And of course, with this transistor off, there was really nowhere for this energy to go. The only other component that it was connected to was the battery. And so what would happen is there was a fairly long relaxation time between pulses as far as duty cycle goes. The on time for the duty cycle of this was probably maybe 5 or 10%. And so there was a fairly long period between the back pulse and the next forward pulse when the transistor turned on again when the magnet came around. So let's take a look at the claims made for this very interesting design. Now, normally I would dissect a patent for extreme minutia, but in this case, the opening sentence has everything we need to know. And it says, this invention relates to electric motors, and more particularly to a novelty electric motor, which appears to have no source of power. Now, certainly, in a country where patenting a perpetual motion machine is essentially illegal, this is about as provocative a statement as any inventor would dare make. And the fact is that Roger Andrews makes this statement for one simple reason, and that is that when you do the math, when you figure out how many amp hours of energy are in the battery, and you figure out how many pulses it puts out from the inductor to drive the little top around the table for 6 to 8 months. What you find is that the toy runs for somewhere between 2 and 3 times longer than it should. In other words, it appears that something is being kicked back to the battery because the battery just lasts a ridiculously long period of time, something that is way beyond anything that could be understood. So, the other thing I'd like to show you is this. So here for figure 10, we see that this is also a very, very good circuit for driving a little pendulum, so it's good for clocks and things like this. But here, figure 11, now all of a sudden, this isn't a toy. He's showing that this can be made into a motor that can drive a generator and all kinds of things, and that this has implications for power production that are really soft-pedaled in the patent. Now, Roger Andrews' simple circuit relates to a family of circuits that are similar to it. And one of the most similar is the standard DC to DC step-up converter. We see that it has a single inductor and a single transistor. And the supply here could be a battery or anything else. But in this case, instead of being triggered by a magnet going by, this is just triggered by some sort of pulse train. And instead of trying to kick the energy back to the initiating battery, what this is trying to do is actually build a charge to a higher voltage over here. So just by setting the circuit up in this way with a single extra diode, then the voltage can be multiplied from our initiating source. So this is another very simple one transistor, one inductor circuit, which has energy kickback similarities to Roger Andrews. Now, certainly no one has done more work on this simple little phenomena of charging an inductor, getting a little bit of motor torque out of it, and capturing the inductive collapse than John Bedini. This is the cover page of his 2003 patent for what he calls the monopole motor. And let me show you that schematic right now. So here is the design of what John calls the monopole motor. And he calls it the monopole motor because on the wheel here, that is the motoring member, only North Pole magnets face outward. And so this inductor is only being subjected to North Pole magnets, and the souths are kind of inside the wheel here, and they never interact with the inductor. So here we see that all of the functions are separated and distinct. So we can see the full action of this simple type of arrangement that was at least partially embodied in Roger Andrews' executive desktop Novelty. We see a battery, and we see a number of coils on the inductor, and in this case there's 3 separate coils, and they're all wound tightly together in what's called a trifilar winding. So there's very tight induction between the windings themselves. We have a movable wheel here. Andrews used either a top or a little pendulum or something else, but John says, no, this is just a wheel that has magnets on it and can be looked upon as a motor. And so what happens is that the magnet will come by here and magnetize the core. And when it starts leaving, what it does is it induces a signal in this trigger winding, which turns this transistor on here. When that happens, the battery conducts current through the coil, through the transistor, and back. That same simple inductor transistor battery arrangement. And in this case, it reverses the magnetism in here and further kicks the magnet out. So in this sense, it works just like Andrew's silly little Novelty. But now there's a whole provision here to capture the energy when the magnetic field in here shuts off. And so here we have a third coil connected across a full wave bridge rectifier to charge this little capacitor. The idea ultimately is to charge this battery, and so when this capacitor gets up to a certain voltage above the battery, then a little, some sort of little timing mechanism, this is shown as a commutator and brushes, will drop the contents of the capacitor onto this battery. So this battery charges, the motor motors, and this battery runs the situation. So here we see the beginnings of an understanding of what we thought might be possible when we saw how an ordinary motor works. In other words, there's an electrical input, there's a mechanical output, but there's also an electrical output. And now here we see the topology where all of these things are working as stated, all in the forward direction, so that we can really understand these things very clearly. So here we have a simple diagram where we show all 4 of these ideas right next to each other. First, over here we have Roger Andrews' simple little toy motor where a magnet comes by, causes an induction, turns on a transistor, and it produces a pulse back out. And somehow some of this energy, even though there doesn't seem to be a current loop here when this is off, some of this energy seems to be forced back into the battery to make it last a very long time. Down here we have the DC to DC converter, and here we clearly show that the battery is charging and discharging an inductor, and we have some sort of little pulse train turning our transistor on and off, and then the current is all shunted over and charges this capacitor here. So again, these things are getting very, very efficient. You can buy little chips now that operate in the 93-94% efficiency for little circuit boards and things for DC to DC step-up situations. And this is a boost converter. Here we have John Bedini's basic circuit. This is the circuit that's been all over the internet for quite a long time. And this is what would be called the simplified schoolgirl motor patent. And again, showing the very extreme similarity to a simple DC to DC converter. Got the battery charging an inductor, turning on and off. You've got a winding that shows some sort of feedback mechanism when the mechanical trigger comes by. And then instead of having a common ground between the supply and the eventual collected energy, he shows a split situation so that basically this battery and this battery are not in parallel, they're actually in series. And so what happens is that this, over here in the DC to DC converter, this draws power all the time. So whether this is charging the inductor or discharging the inductor, current is coming out of this system all the time. Whereas in this situation, it acts more like a bucket and dipper system, where a charge will come out of this battery, it will charge this inductor, and when this shuts off, that ends the current loop with the charging battery, and then this becomes the source, and it discharges into this battery. So it basically it scoops some energy out of here, invests it in creating the magnetic field. That magnetic field then can do work on the wheel, and then when this turns off, this discharges and is as much of it as can be recovered and is put into the second battery. So now let's take a look at Bob Thiele's circuit and see if any of these types of activities could be going on, and it looks like they could. Here he has his basic mechanical contactor as a commutator here, and so when this is shut, the solenoid will not only act as a snubber arrangement to suppress sparking here, but it can also act as a small storage system that can transfer energy in an AC pulse. So if this charges up to many times higher than the battery, and then so if this is positive and this is negative, then this is going to be the negative side of the capacitor, and this is going to be the positive side of the capacitor. So this side of the capacitor rises to many, many times the battery voltage. And so it's possible to transfer a pulse of current in the charging direction back to this battery using this circuit. So it is possible, when this system turns off, that this system can kick back some of the energy back to the battery to make his battery last a very long time. So this may be one of the things that Bob Thiele was doing to make his motor perform with the superlative performance characteristics which he was describing. Now, we saw on the bench that you could get a certain amount of the electrical energy back out of the machine. But to get up to the level of performance that Bob Thiele's talking about here, we probably have to look very carefully at his solenoid design as well. Because we saw that the more you folded the magnetic energy down into a closed path around the movable member, the more mechanical energy it produced without having to put any more electricity in. And we saw that on the bench. So let's suppose, and let's imagine that Thiele figured out how to maximize this process, and that is a very, very important aspect of why his solenoid engines worked so much better than anything else anyone else has ever reported. So here is a close-up shot of one of the four-cylinder machines, and we see here the solenoid, and we can see a couple of things. One, we can see that the movable plunger comes out essentially or up to the top at the end of the stroke. And we can see that the coil is completely enclosed in a magnetic keeper, and that the dimension across the keeper to the movable plunger, it looks like the movable plunger is approximately 1/3 of the diameter of the total solenoid. So let's take a look at some other photographic evidence. So here's a side shot of the 8-cylinder Magnipulsion engine model. And if we just zoom right in here, we can see that we can look down the throat of these little solenoids here, and we can also see a side view, and we can see the crank system here. And what we see is that it doesn't look like that these are built on the design from the second patent. And in fact, it doesn't look like that they are, that the movable member ever comes out of the structure at all, that this is just the connecting rod in any of the positions. And again, we see that the magnetic keeper looks like it's about 2/3 of the diameter, and the movable plunger is about 1/3 of the diameter. So this suggests that the design that we tried in our motor, based on the drawings from the second patent, really weren't what he was doing. So let's go back to the first patent, because in the first patent there's another drawing that shows a different construction. So here is figure 5 from the first patent, and this looks a little bit closer to what we were seeing in the photographic evidence. The main discrepancy is it doesn't show an open top here, but for the most part it does show that the movable plunger kind of stays within the structure, and that up at the top here, when the throw is all the way to the top, then the connecting arm would be rather deep inside the structure. So let's take a look at one other drawing as part of the first patent. So here are figures 1 and 2 from the first patent, and what I'd like to show you here is if we come in on a real tight shot, we can see that the solenoid design here is much more similar to the drawings that I just showed you, and the actual physical photographic evidence which the pictures of the working model shows. So basically what we have here is a solenoid piece that stays deep within the structure for its entire movement. And so now what we need to do is we need to understand how he gets these solenoids to create so much physical mechanical energy. So let's take a look at the probable internal design of this system. Now we know from the earliest reports of people trying to develop a magnetic attraction engine that the magnetic force only creates a very large physical force when the air gap is the smallest. And the best and the brightest motor designers of the last 170 years or so struggled with getting the topology right. We're quite clear that Bob Thiel figured this out, and here is essentially the essence of what he found. By essentially adding this little extra lip at the top of the keeper here, what we see is that we can turn the coil on at this point. This is the midpoint, the point at which you're at the midpoint on the crankshaft. In other words, where you can apply the most direct tangential force to the crank. And when we turn the coil on at this point, essentially the magnetic keeper is already completely made. In other words, the magnetic field can act at the closest possible range. And this means that the force on our movable plunger here is going to be maximum right from the start. But because there is slightly less iron down at the end here and slightly more iron up here, moving upwards will allow for the creation of an even more advantageous magnetic circuit. And so that is the direction of the force generated. So let me just back out here and let's just take a look at the entire design of the Magnipulsion solenoid. So we saw from the photographic evidence and from the diagrams in Thiel's first patent that the movable plunger never really leaves the structure. So here at the bottom dead center of our crank, we can see that the plunger is essentially at the bottom of the structure. And here at top dead center of the crank, we can see that the plunger is essentially at the top of the structure. So that the plunger basically moves within the structure and it stays within the structure at all times. And this keeps the physical side forces and other things at a minimum so that a relatively low friction sliding movement can be generated in here. So what we want to see here is that the situation is designed so that the coil would be turned on when the plunger is halfway through its movement, and because at that point we can apply the greatest tangential force to our rotating member. And to do that, we need the magnetic circuit to be already in its condition where the least air gap exists between the moving member and the non-moving member, and that the moving member can move in such a way that it produces an even more advantageous magnetic circuit as it moves forward along its path. So these are the fundamental conditions which allow the Magnipulsion engine to produce tremendous amounts of mechanical energy for the electricity applied. Now, let me give you just a quick example of what I'm talking about here. We saw in the commutator circuit that his contact, the magnetic field would collapse again, and that electric pulse could be recovered. So it's important to see over here in the full extension drawing here that this is where the solenoid is trying to get to. We know that if you take any kind of movable piece of iron and put it in a coil, it will always try and center in the coil. And this is true whether there's a keeper there or not. And you can run as many experiments as you want, but the fact is that the keeper, or the movable piece, will try and center itself within the coil. So when we turn it on here, it's trying to get to this position, and it will, if we just left the coil on, it would rise to the top and stay there. So this is the basic secret. This is the fundamental design of Thiel's system, and my reproduction of it, my reconstruction of it. But even if this wasn't the exact design that he used, his design fulfilled these requirements, and therefore it is essentially the same. So now we can put all the pieces together and come up with what I'm calling here for this purpose the Lindaman solenoid engine, because this has features in it which I derived from a number of different sources. First of all, we see that we have this basic structure and we have a crankshaft, but that this, when it turns on, the magnetic field's already made, so we can expect that this solenoid is going to give us the biggest bang for our buck when it comes to producing mechanical energy. We have a very simple circuit here, and this is the run battery, and it goes through the coil and a single transistor, and then back to that battery. And then we can control when it is on using a commutator arrangement, and this commutator could be a brush, or it could be a magnetic reed, or it could be an opto-isolator with a shutter, or anything like that, and or a P device of some sort that was controlled by something else. And then we just have a voltage bridge, 2 resistors here that put a little bit of positive energy on when we want to. And when this shuts off, then this is just a connection back to the negative. So this would clamp the transistor off very rapidly when the commutator lit off. So now if we simply apply electric energy in this quadrant here, so we can pull up here, and then we discharge electric energy in this quadrant here, so the magnetic field is rising and collapsing, and we can use the entire magnetic field to cause our attraction process, because it doesn't matter whether it's delivering current or whether it's running on current, the magnetic field is there, and the ampere turns are there, and so we can power this motor now not only from the energy that is coming from our run battery, but also it can run on the energy that we are returning to the second battery, because the field is the field, and the field is causing a mechanical attraction process which doesn't really alter the electrical processes much at all. So here is a very, very high COP, zero back EMF electric motor. So learning from Bob Thiel's success, we can now take the idea to its full manifestation of a rotary design and get back to a true motor instead of running it like a piston engine. So here's what I call the Lindaman rotary attraction motor featuring the S rotor. And let me just zoom in a little bit and so we can get a closer view of the structure. Basically, we're using the same circuit as we were with the solenoid engine in the last slide. But now we've replaced the piston and crank mechanism with this. And this basically is just a single coil with a C type of core and what I'm calling the S rotor. And the S rotor is just made out of iron. It could be cast iron or Selectron laminations. Anything that will magnetize to a high degree but then let go of its magnetic field completely when the impressing field is gone. And so what we see is, like the extensions coming down into Bob Thiel's solenoid design, what we have is basically an iron beam here, and we know that if that's all that was there, if we turn this coil on, this would want to rotate around and come in line with this. But now what we do is we put 2 arcing extensions onto that, and we make it thinner and thinner and thinner out to the edge. And the reason we do that is what we want to do is we want to produce 2 effects. The first is that we want to give the magnetic field a path through iron 100% of the time. So for instance, if we turn the coil on right here, there's only these 2 small air gaps right here, so the magnetic field in the iron or in the movable piece can be maximized. Secondly, what we want to do is we want to make sure that the magnetic force creates a tangential force on our moving member, and here again, as long as we sweep these way out to the end, we can get a very strong tangential force when the coil comes on. And of course, what it's going to want to do is, as the magnetic field is established in here, it's going to want to create what's called an attraction action, and that means that the lines of force are going to want to get shorter. That's what attraction is. Attraction is the lines of force between 2 poles getting shorter. So the lines of force in this situation, they're 100% in iron, but they can get shorter, and they can get shorter by rotating this beam around until this member here is straight across here. That would be the shortest path. So it's going to do that, and it's going to do that with extremely strong forces, and they're applied to our rotor in this case in a completely uniform way, so that all of the forces are balanced on the beam, on the bearing system and on the shaft. All of the forces are evenly distributed, so that the only real weakness here is that, of course, when this thing comes on, it's going to want to just bend these arms outward. So that's basically the only weakness in the design, and of course that can be mechanically restrained. So that's the one small concession we make to this situation. And so what we're going to do is we're going to, let me just widen up this shot again. So what we're going to do is we're going to turn the magnet on in this position, and then we're going to allow the rotor to rotate approximately 45 degrees until this beam is approximately in this position. And then we're going to turn the power off. So we let the magnetic field rise in strength to that point, and at that point we let the magnetic field discharge. And again, we have the same run battery through the coil, back through just a single on-off switch, back to the battery. And now our commutator can have 2 on strokes per cycle, or per revolution, because we have a situation where the rotor is symmetrical at 180 degrees, and therefore we can, every time we go around 1/2 of a revolution, we're basically in the same position, so we can do it again. So when the coil discharges, of course, it discharges back to recharge this battery. But essentially now what we've done is we have accomplished everything that we had hoped we could accomplish when we looked at the back EMF problems in our initial traction motor. And that is that the electricity event is happening here in the coil, so that when we put the electricity into here, that's happening here in the coil, and when we get the electricity back out, that's happening here in the coil. Meantime, over here is where the mechanical energy is produced, so now we have created a physical separation so that the mechanical energy is being produced in a different member by a different process than the electric induction. In other words, this is just being attracted by this field when it is present, and that field is present as long as there are ampere turns. In other words, as long as there's amps moving in this coil, there's a field here, and so we can get if we put in power to this point. So the inductance of the coil here will cause a current ramp that will have some duration. And let's say it's 3 milliseconds until we can, when we apply at this voltage, until the magnetic field strength is approaching our optimum point. At that point, we can shut the transistor off, and because of the inductance and because this battery is essentially similar to this battery, then this will discharge in a similar time frame. So let's say this charges up in 3 milliseconds, and it will probably discharge in about 2.5 milliseconds. So now we have a magnetic field here. There are ampere turns in this coil for a total of 5.5 milliseconds. So that is the period during which we can get an attraction cycle and convert that to mechanical energy. We can see that now we are producing mechanical energy strictly by the action of the magnetic field, and so that's indirectly in relationship to the electrical input. So again, we've created a more of a separation between these two events. We've made them happen in different components using different processes at different times. So here we have finally realized our hope that we saw hidden within the traction motor or the induction motor at the beginning of this movie. And so this solves the fundamental problems of the electric motor. We can produce tremendous amount of mechanical energy here. It is only indirectly related to the amount of energy that we put into it. When we load this, it will slow down. But what we can do is, if we can design this, we can impedance match all of these things so that, let's say, we want to run our loads, let's say at 3,600 RPM. What we can do is, we can set up the rise time of the inductor and everything so that it matches that speed point. In other words, so that we get to our maximum point here and collapse when the rotor is turning at that speed. So when it speeds up to a higher speed than that, what will happen is that it'll start cutting off before it gets fully magnetized. And so then this will, so as it speeds up from this point, it'll start drawing less and less power, like an ordinary motor. And then you can, when you put a load on it, it will start magnetizing to a higher and higher and higher and higher degree until it gets to this maximum benefit point. So it will rise, the magnetic or the mechanical energy creation will rise into the load as it slows down to meet this perfect point, at which point it can deliver power at its maximum rated speed. And so all of these things can be engineered into it so that it will have similar characteristics to a normal motor, but still run on these principles. So here we have a situation where we can put a certain amount of energy in, probably get at least 85% of the electricity back out, and we can create motor torque on both what we put in and what we get back. So this is the secret of the electric motor of the future, and there's only a few other things I'd like to show you at this time. So let's do a quick COP analysis of our new motor topology. If we assume, in system assumptions here, if we assume that our electrical recovery can be 85%, and 85% for a DC to DC converter or one of these systems is certainly achievable. Many people have built systems based on John Bedini's ideas where recovery is higher than this. So let's also assume that our mechanical energy production is approximately 70%, which basically means we can produce 70% mechanical energy from our electrical input. Now, obviously, this is all totally under unity. This is not an over-unity machine. So let's take a look at a hypothetical COP analysis. If we start with an electrical input of 100 units of energy, and we can get 85 units back, then our net electrical input here is only 15 units of energy. If our mechanical energy produced is 70% of the total magnetic field available for the attraction process, then the attraction process, the total magnetic field over here, is equal to our input and our output. So this is the total magnetic field. So we have 185 units of magnetic field energy. So if we have 185 units of magnetic field energy times our 70% efficiency, we get 129.5 units of mechanical energy produced. If we divide our output by our input here, we see that the machine is capable of producing a COP of 8.6. Now, this is starting to look good. Remember, the COPs of our permanent magnet field induction motor was 0.25. So this is something on the order of 35 times better COP than the off-the-shelf motor. Now, I was introduced to the work of Bob Thiel in 1979. By 1983, I was working in Santa Barbara with a group of people on a number of these ideas. And here are some documents from my files this was drawn in June of 1983, but this motor was fully designed and conceived of by March of '83, and I was calling it the flux motor at the time. And you can see here in this diagram, or in this piece of paper here, the opening statement says, an electromechanical device to convert magnetism into useful work and electricity. You can see the basic idea here. We were going to use C cores of like transformer laminations, put a pulse of DC into it, attract the iron piece, and then turn the power off and get the pulse back by transformer action. And so you can see over here in the diagram to your left, we have 4 of these C-type cores. This is a top view, and the rotor had 5 sections, iron sections in it, running the full length of the C core, and these would just rotate in. So if this coil was turned on, it would very rapidly attract this iron section into alignment. So the on time here could be very short, turn on, turn off, and get the kick back. This had a mechanical brush-type commutator. And so the combination of 4 coils and 5 sections on the rotor meant that there were 20 individual attraction strokes just to get the rotor around one time. And this motor was just ferociously powerful. Unfortunately, it was under development right at the time we were in the process of trying to raise money, and we were unable to raise any money. So this system was never fully developed. Here's an actual photograph of the model of the flux motor that we built in 1984, and you can see the brush commutator on the top here and the 4 coils going in towards the central member, and the rotor was deeply embedded inside here. So this is the photograph of the only working flux motor that we built at that time. This is myself and the machinist who built these amazing machines with me, Michael Knox. Here we're testing a variation on a similar 4-coil arrangement. This is set up as a variable reluctance generator, and it's powering the light bulb bank on the side from this normal type of motor. So we were working on the development of a special kind of motor driving a special kind of generator to produce a power plant. So here then we see the S rotor applied to the flux motor topology, where we have 4 of these C-type coils and cores arranged around. This is a top view, and this is a side view. And so these coils can turn on and advance the rotor until it's 90 degrees past here. And then these coils can turn on and advance it the next 90 degrees and so on. So this is becoming the beginning of an engine where the power is applied most of the time. Obviously, the magnetic forces are kind of moving in pulses, but still in all, the total amount of mechanical energy produced by an engine of this type is very significant. And using the circuit that I showed, or some other variation, or some other methodology, a very, very high percentage of the electrical energy can be recovered while producing tremendous amount of mechanical energy. Well, now you know. Today's electric motor holds a variety of secrets. The first big secret is the true function of the back EMF. We saw, and I carefully explained, that the back EMF is neither a reflection of the mechanical load on the motor, nor a convenient method to make the motor self-regulating. Its real function is to destroy most of the energy that the operator is forced to apply to run the motor without creating any benefit whatsoever. The back EMF in a motor is nothing more than the recognition that the direct induction electromechanical machine is always a motor and always a generator, and that these two opposite functions cannot be separated in this design topology. Its performance is not limited by the laws of physics, but rather by the behavior of the forces as they are constrained by the geometry of the design. The second big secret is that motor designs that produce no back EMF have been around for 170 years, but they've always been described as being archaic and inefficient. These designs use a single electromagnet to attract a piece of iron and never use permanent magnets at all. In the 1970s, Bob Thiel studied this process in depth. He eventually solved each and every one of the historic design problems that limited its mechanical energy production. In the process, he built and tested the most powerful electric motors ever designed that ran on magnetic attraction. The third big secret is that electric motors run on DC pulses can be configured to return up to 90% of their input electrical energy without affecting the production of their output mechanical energy. Roger Andrews stumbled into this process in the early 1970s and successfully marketed a bunch of toys. But John Bedini independently discovered this process, and after 30 years of in-depth study, perfected and patented the simple circuitry that allows this to be understood and maximized. When all of these discoveries are put together, the electric motor emerges as an astonishing machine with unparalleled power and performance. I showed you a number of my own designs that bring these ideas together. But these concepts are universal and can be applied to hundreds of design topologies. Even more exciting is the fact that electric generators can be designed to provide no back EMF operation as well. The possibilities are without precedent. Quite simply, we're on the threshold of a new electric age. We're being told that our planet is warming up and that we must reduce the amount of CO2 released into the atmosphere. Increasing the efficiency of electric motors is one way to help. I encourage each and every one of you to experiment with these ideas. Thank you for your time and attention.